The nodal analysis approach to solve circuit equations uses nodes as the state variables. It is a common practice to describe a device as something what we call a lumped circuit element. That is, we assume two nodes are connected by simple circuit elements like resistors, capacitors, and controlled sources. This approach works well for simulating transfer functions at low frequency, but it may not be enough for simulating high frequency or fast transient circuits. The problems encountered at high frequency is quite different from that what we know at low frequency. In this video, I'll explain the challenges of high-frequency simulations and discuss the approach to develop high-frequency models. Let's recall what we learned from the video on frequency domain simulation. The first step is to solve DC biasing points. Therefore, the frequency domain model should include a DC transfer function model. As we discussed earlier, capacitors are treated as open circuit while inductors are treated as short circuit in DC simulation. It can potentially lead to convergence problem due to floating nodes. A good example is given here with a circuit resemble a MOSFET model. The voltage Vx from the capacitor voltage divider network has no solution if the capacitors are treated as open circuits. There are different approaches to solve the problem. For example, a transient simulation with a constant input can be performed to obtain a value of the capacitor charges, which in turn determine what is the voltage Vx. Solving the DC biasing point has been discussed in other videos, and it is not the focus here. Once the DC biasing voltages of all the nodes are solved, we can use their values to calculate all the conductances, capacitances, and in some cases inductances at the given biasing points. These are linearized values and can be treated as constants at the fixed biasing point. They are then inserted into the Jacobian matrix, which is evaluated in the frequency domain. The frequency, or omega, serves as the running variable in this matrix. Since all the values are fixed at each frequency point, there is no need for iteration in this simulation. If you would like more information on the simulation procedures, please refer to the previous videos on frequency domain simulation. Let's use an example here to illustrate the characteristic for AC simulation. Consider a MOSFET biased in the circuit given here. The two batteries provide the DC biasing, and the AC source serves as a small signal unity input. The current measured at the output represents the trans resistance, or the gain, is plotted against the frequency of the AC source. The output is similar to what is given in this figure, with the frequency plot in log scale. The MOSFET initially provides a high AC current gain. When the frequency increases and becomes so fast, the output current cannot follow the input, and the gain or magnitude of the output current variations will drop. However, many earlier models failed to predict this simple behavior. Typical level 1 model produces a flat frequency response curve as shown in the given figure. When a long transistor is broken down into two identical ones in series, the IV characteristics are expected to be the same according to the classical model. However, as pointed out by Yanis Zouvydis, the two simulations produce very different frequency response with the simple model. The question is, which characteristics is physically more reasonable? And what is the cause of the discrepancy? If we examine the physical structure of the channel of a MOSFET, it is composed of a distributed network of resistors and capacitors as shown in this figure. In order to fit into the framework of the modified nodal analysis, the distributed nature of the MOSFET channel is simplified to simple lumped RC network. The model representation follows the topology given in the capacitance model after linearization for frequency domain simulation is given here in this picture. In such representation, there is no resistance for the current paths from the gate to drain and gate to source terminals. Therefore, there is no delay in the response at high frequency from the gate to the source and gate to the drain nodes. As a result, the response will not drop even at high frequency. This example illustrated that the lump circuit model is not good enough to represent the distributed nature of the channel RC network. We can implement the distributed network topology of a MOSFET channel by adding internal nodes. It improves the accuracy of the frequency response, but may lead to significant delay in the simulation time due to increase in size of the Jacobian matrix. It may be acceptable in frequency domain simulations as no iteration is needed. However, the delayed add to transient and DC simulation is usually not acceptable. As a compromise, some models may use the lump circuit models for DC and transient simulation, but switch to the distributed network when performing AC simulation. This solves the problem by providing additional accuracy required by frequency domain simulation, but it causes some concern to the model developers as the frequency domain model is no longer consistent with the DC and transient simulation model. When the MOSFET is broken down into two shorter transistors in series, some internal current paths colored in red will have delay to achieve equilibrium, leading to a drop in the output response. The topology becomes closer to that of the distributed network in the MOSFET channel. If the goal of the model is just to approximate the behavior of a MOSFET at high frequency, we can modify the lump circuit model to retain the first pole in the distributed channel. This can be done by adding two resistors in series to the gate-to-drain and gate-to-source capacitors to represent the delay due to the channel resistance. This requires only two internal nodes, but able to retain the dominant pole in the distributed MOSFET channel RC network. Or an even simpler method is just to add the gate resistor to generate the delay due to the dominant pole of the distributed network. By adjusting the resistor value, the location of the dominant pole can be matched. The process ignores all the high-frequency poles, but it is acceptable as we seldom operate at transistors beyond its unity gain frequency. At the same time, the practical operation frequency of the transistors of many circuits are determined by the external components that they are connected to. This implementation will not affect the behavior of the DC model, as the resistance is in series with the capacitor. However, the picture may result in a confusion that the newly added resistance is coming from the polysilicon gate resistance. In fact, it represents the channel resistance from the gate through the channel to the source and drain terminals. To further refine the high-frequency model, other parasitic elements may need to be included. For example, there will be AC current path through the substrate. In some of the BC model, a substrate-resisted network is added to the MOSFET model with 3 internal nodes to capture the substrate-related frequency behavior. We have explained the difficulties to develop high-frequency model. The distributed nature of a physical device not only affects the formulation of the high-frequency domain model, but also the behaviors of the transient model during fast switching. In transient simulation, charges are associated with the terminals, and the charging and discharging of the terminal nodes contribute to transient currents. In the formulation of the transient model, the quasi-static approximation is assumed in deriving the charge model. That is, we assume that all terminal charges only depend on the instantaneous voltages at a given time. As long as the voltage is known, the value of the charge at all terminals are fixed. However, it may not be the case. Let's look at the given example. When a MOSFET is being turned on by an input pulse to the gate, we look at the channel charge distribution at different time points, T0, T1, and T2. T0 refers to the point right after turn on. At T0, there is no charge in the channel, as the MOSFET is at the edge of turn on. The channel remains off, and the channel inversion charge is 0. If the ramp is low, the sampling points or the integration time points can be very far away from each other. At T1, the sampling is taken long enough for the charge in the channel to achieve equilibrium. The channel charge achieves its steady state value denoted by the inversion charge at Vg in the picture. This charge has no time dependence. However, if the input is extremely fast, as shown in the figure, T1 is forced to sample the signal at a time very close to T0. At that point, the equilibrium cannot be achieved, as shown in the picture. The quasi-static assumption that assumes the channel charge will reach equilibrium at T1 will not hold. Even when the gate voltage stops changing, as in T1 and T2, the amount of charge in the channel will still vary as the charge is trying to reach equilibrium. So even though the gate voltages are the same at T1 and T2, the amount of channel charge is different. The terminal charges, therefore, are not only dependent on the terminal voltages at a given time, but also a direct function of time under fast ramping. The quasi-static approximation is no longer hold. The breakdown of the quasi-static approximation at fast transient leads to the so-called non-quasi-static effect. The terminology is quite misleading, as non-quasi-static behavior is not an effect. It is just a result caused by the incorrect quasi-static approximation used in SPICE. Some people also use the term frequency domain or high-frequency non-quasi-static effect. Strictly speaking, it is incorrect, as all frequency domain simulation is based on steady-state biasing point solutions to linearize the RC network. That is, the nature of the simulation is under a quasi-static setup. If the output fails to match physical data at a high frequency, it is just because the lumped circuit model does not have enough circuit element to capture the distributed nature of the channel. To study what is the problem under fast transient, we can look at the common MOSFET output using a simple MOSFET model at fast turn-on. In SPICE, the current through the MOSFET is composed of the DC current as a function of the node voltages, plus the charging currents due to the increment of the terminal charges between the previous time point to the current time point. It is illustrated by the equation here. The DC current is coming from the current model, and the charging current is coming from the charge element in parallel to the resistive component. This equation is not entirely correct, and I'll explain it later. I'm just going to explain the behavior of the SPICE model here. When a ramp is applied to the gate of a MOSFET, the DC current and the charging term as a function of time is given in the figure here. The DC current is just the normal transistor current that we are all very familiar with. For the charging current, it is 0 below the threshold voltage in the simple model, as there is no inversion charge. After threshold, the charge is proportional to Cox Vg minus Vt, and its exact value depends on the charge partition schemes discussed earlier. So, the charging current, which is given by the charge derivative, is proportional to Cox dVg dVt. Note that the charging is achieved by having electrons moving from the source and drain to the channel. Therefore, the current is moving out of the drain and is considered to be negative. After T2, Vg is no longer changing, and dVg dVt is back to 0. If the ramp is slow, the charging term is small due to the small dVg dVt. The output current is just similar to the DC current. When the ramp rate is very fast, the charging term can be very large. Then, the total current given by the sum of the DC current and the charging current will look like what is given in this figure. So, an abrupt negative charge in the current is observed at Vt. This is the so-called non-quasi-static effects, and you may refer to the given reference for the details. Physically, the current should look like what is given here in green color. Before the channel is formed, no DC current flows through the channel due to the high channel resistance. At T1, the gate voltage is beyond Vt, and the channel is supposed to achieve equilibrium condition under the quasi-static assumption. Therefore, a positive DC current is expected. However, if the ramp rate is very fast, the charge may not be able to reach equilibrium, and the channel is only partially formed. Without a continuous channel, there is no DC current, and IDC should be 0. For the charging current, we assume that there is a high drain voltage at the MOSFET. The MOSFETs were initially operating in the saturation region. In that case, there is a pinch-off region at the drain, cutting off the drain terminal so that the channel charge is mainly coming from the source. Therefore, the charging current from the drain terminal is also 0, leading to a 0 drain current. From this example, we can see that the quasi-static assumption used in Spice's equation to compute the source and drain current by the equilibrium current plus the charging current is inherently incorrect. The so-called DC current is dynamically changing with time and cannot be assumed to be static. Given more time beyond T1, the charge from the source reached the drain and established the channel. Both the direct drain current and the charging current from the drain start to contribute to the total drain current. But the values are given by the transient charge and cannot be calculated with any equations based on the steady state conditions we derived earlier. After the ramp stop at T2, the channel charge still not yet at equilibrium. So the channel keeps charging until the direct current reaches the equilibrium value and the charging current will go to 0. What happens if we add a resistor to the gate to account for the delay in the channel charging effect, as in the case of frequency domain simulation? It will not affect the DC equilibrium current calculation, as all the gate voltage will drop at the oxide capacitor. However, the charging current will be smoothed out due to the added delay. It is getting closer to the real drain current with a delay adjustable by the resistance value. However, it still produces a non-physical negative current after the VT, because this approach did not account for the pinch-off effect at the channel region near the drain. To summarize, the quasi-static formulation in Spice may break down at extremely fast switching in transient simulation. The question is, how serious is the problem? It turns out it may not be very serious. For a self-driven circuit, the speed of the input signal is limited by the previous state's response. So, a circuit is unlikely will be driven by an input faster than its own response. It will only happen when some very fast switching element is driving a large transistor with slow response. Even when this happens, the effect is usually not very obvious because the loading capacitor as well as the interconnect delay will slow down the signal at the input. To really demonstrate the problem, we have to use an ideal voltage source with almost a step function input to a transistor, which is not very realistic. Therefore, even the formulation in spikes is incorrect. It can still be used to approximate most of the practical situations, as long as we are not operating a transistor near its cutoff frequency, at which the transistor fails to function. One more consideration is being left out in the discussion so far is the effect of charge partition scheme mentioned in the previous video. For example, if we use the 0-100 charge partition scheme to remove the non-physical negative drain current by associating the channel charge only coming from the source, then the drain current will just be the DC current. But this will give a wrong delay to the drain turn on. Even worse, it will just push the problem to the source current, which is shown in the figure. The charging current pulse will appear at the source and be magnified. If the purpose of the simulation is to get the delay of the circuit, the 4060 charge partition model is closer to reality, as shown in the figure here. Therefore, it is the most often used charge partition model. But the negative current pulse due to channel charging current can still be observed if the ramp rate of the input pulse is fast enough. To handle fast-switching circuits, the most appropriate approach is to reconsider the incorrect quasi-static assumption used in spikes. But it is difficult, as it has been used for quite a long time. As an approximation, we can divide a large transistors into many smaller segments. It will more accurately approximate the physical structure of the transistor, but it will significantly slow down the simulation speed due to the increase in internal nodes. Or we can combine a distributed network as a black box and derive the characteristics at the terminals of the black box. It is like solving a complex circuit equations without relying on the iterative power of spikes. The model will become very complicated. Furthermore, the accuracy of the fast transient simulation is subject to the uncertainty in the source and drain charge partition, which is a problem still unresolved today. So, there is no good solution for a robust simulation of high-frequency circuits under the current spikes framework. However, the good news is, when the size of the circuit becomes bigger and bigger with many nodes, the nature of the circuits become more distributed, and the problem caused by the NQS effect may not be observable. But this is a very important piece of information to keep in mind as a model developer.